Hi, everyone. Hope you had a good first week of classes. Hope you're settling in and that you're still staying safe and being healthy. Um, this week's lecture is going to be a two-parter, and it includes two topics that are relatively brief in terms of the content, but really important for you to understand and orient us towards the content that we're going to be learning about and talking about for the rest of the semester. So the first topic I want to cover is science. And as you can see from this picture of Hugh Jackman, who's very excited about science, I am also very excited about science. But from my experience as a professor and as a student and as just a person out in the world, I think science is very misunderstood. And so I want to spend a bit of time making sure that we're all on the same page about what science is, what sorts of questions it's designed to answer, and how it can be used, and what are some of its limitations. So let's get right into it. And of course, the first question is, what is science? If we were in class, I would ask the question, who is this person and what are they doing? This person's a chef. Her name is Kat Cora. And then the question is she doing science in her profession? She's a professional chef. And of course, the answer is yes, right? And so, what is science? Science is an evidence-based process of attaining knowledge. But there's another caveat to that definition that's really important, and what I think separates science from other evidence-based processes of attaining knowledge, and that is the evidence that's used to define knowledge must translate across human culture and personal experience. And that's one of the things that's really which makes science unique is that you don't necessarily have to have a deep cultural or personal experience with the evidence to accept an idea that science is offering. There are other ways of knowing that we'll talk about in a bit where you cannot understand the knowledge and you can't relate to the knowledge if you weren't deeply indoctrinated into the culture, or if you don't have a really profound personal experience with that. And so that's what I'm talking about in terms of the differences and different ways of knowing. Science, it's something that most people can understand, most human beings can understand, and it doesn't require a lot of context to put your mind around the ideas that are being expressed. And so here's a picture of a farmer. And of course, farmers are doing science. The process of farming, the process of cultivating plants is science. It's evidence-based. And because so many different human cultures practice farming, and many human cultures grow the same things and do the same things, we see that that base of knowledge is scientific because it translates across human culture and personal experience. It does get into some gray areas depending on different practices, but just the simple practice of cultivating food is science. So why is it important? Why is science important? And of course, it's important because it helps us understand the world around us. And as I mentioned before, it's not the only way that we understand the world around us. It's just one particular way, but that is very useful. And it helps us to share our understanding, especially across different cultures and different experiences. And again, that's one of the utilities of science, is that it can be shared very easily. You can sort of think about science as the dollar when it was actually much more robust. It's something that no matter where you were in the world, people understood what a US dollar meant, right? You didn't have to speak English, or you didn't have to speak one of the other common languages in this country to understand what a dollar was and that it had utility. And that's sort of the way that science functions in terms of being able to share knowledge and share things across cultures. And then the last question is, who does science? Right? I've already shown you two pictures of people that maybe you wouldn't immediately think of as scientists, and then this last picture of somebody working in a lab, which is maybe a little bit more easy to understand that that person is doing science. But really, we're all doing this all the time. We are all using evidence that can translate across human culture and experience very easily to build knowledge. Again, it's not the only way that we build knowledge, but it is something that we're all doing all the time. All right, so now for some scientific terms that I think are important to separate from how they're used in other realms of knowledge. So, a hypothesis, of course, is a tentative answer to some question, and you've probably heard this definition many times throughout your schooling. So, a scientific hypothesis has two key elements, two things that make a hypothesis scientific. Now, there are all sorts of hypotheses out there, but they're not all scientific. A scientific hypothesis must be testable and falsifiable. And those things are really important when we're talking about knowledge that can translate across personal experience and culture. And that's really what separates science and scientific hypotheses. Okay, and so as I mentioned, not all hypotheses are scientific. But all scientific hypotheses must be testable and falsifiable. And I'll give some examples in a little bit if it's not immediately clear what those two criteria mean or look like. And so one thing that's really important that in the common literature we as a society and across societies don't do a very good job of is using the type of nomenclature that couches scientific knowledge. And so scientific hypotheses are never proven by the evidence. Now, that's not the way that a lot of news outlets and sort of common discussions of science talks about science. And you probably have heard people or even said yourself that science has proven this to be true or science has proven this to be false. And in fact, that's not the goal of science, is not to prove something. The idea of something being proven means or implies that it is an idea that is fixed throughout time, no matter what, right? Like gravity is something that's been proven. But there's a different way of talking about scientific hypotheses that we hold as fact than the common way of saying or talking about science. Okay, and so it's really important to understand this, that scientific hypotheses are never proven. They're either supported or not supported based on the evidence, right? And so we're building space within science to understand that no matter what idea that is present, it's tentative, okay? All right, so there are some things that science has shown evidence for that we kind of take as fact or take as very consistent, and that's when we get into the realm of talking about a scientific theory. Okay, so a scientific theory is a scientific hypothesis with broad application and supported by many experiments. All right, so some theories are accepted as fact due to the overwhelming evidence. So those are some ideas like gravity that we hold as fact because there is overwhelming evidence to support them, or because they have broad applicability in our everyday lives. Okay, but when we start talking about, we'll take a scientific theory like gravity. It's not true, or it doesn't hold. Sorry, that's the wrong language. Not true, but the presence of gravity, or what the theory of gravity tells us about the ways in which matter should interact, is not present. The rules that we think will apply for in a certain realm with matter do not necessarily apply when we're talking about matter as it behaves at the quantum level. Okay, and so there's a realm of existence in which the theory of gravity starts to change, right? The theory of relativity starts to change. It doesn't hold up. And that's why, we never say that science has proven something, because we're always discovering new things, and there are applications that may not be part of our everyday lives in which our ideas do not necessarily hold up. So, this idea of a theory as it's used in different realms in social science and humanities and things like that, mean something very different. So when somebody says that they have a theory of social interaction or a theory within the humanities fields, they're not saying the same thing as a scientific theory. Okay, so in those other fields outside of science, when somebody uses the term theory, they're often talking about what would be equivalent to a scientific hypothesis. All right, and so this question of what happens when science gets something wrong, and this is something that is hotly contested within sort of the public sphere, and oftentimes it comes from arguments around what science says and what science doesn't say, come around not understanding what science is able to say and what science is not often not saying. So, there are many things that have been done in the name of science. All you have to do is look at some really oppressive regimes, Nazi regimes, colonial regimes, in the name of science, people wanting to do awful things to people to determine all sorts of horrible things about the limits of human pain, to whether or not if you torture one identical twin, does the other twin actually feel that sort of thing, right? And a lot of these things, in terms of awful things that science has done or that have been done in the name of science, come from cultural biases or the desire of people who are doing these things to exert power or establish power over other cultures, over other species, and what have you. And that's why the social sciences and the humanities are really important, and why science isn't the end all be all when it comes to generating knowledge, right? We have to be able to uh, take the context of our knowledge and to be critical about the ways in which we're forming those ideas. And social sciences and humanities really helps us do that, okay? Particularly when it comes to awful things. But science can also just get something wrong that doesn't necessarily have, awful consequences for people or human beings or other environments or other species. It could simply be from a lack of information, right? Part of the process of building scientific knowledge is updating these ideas and coming up with new evidence and finding new evidence that forces us to change an idea. We think about the theory of relativity when it was established and the evidence that it showed, and then human beings were able to understand the way in which matter behaves at a much, much smaller scale. We can even think about, I don't know if any of you all have watched the Marvel Universe series and the last couple of movies with, what was it, Thanos and Endgame, I think was the last movie. And how Ant-Man went to the quantum realm and stayed there, and how things got weird in that quantum realm because matter behaves differently, right? So when Einstein came up with the theory of relativity, he didn't know about the quantum realm or how it behaved, okay? And so that theory had to be updated, and those ideas had to be updated. And so science is this process of finding out new evidence and constantly testing our hypotheses and even our theories. So all scientific conclusions are tentative. So if anyone is, out there saying that, science has proven something or that's impossible because science says it's not so, or using science as this kind of end all be all system of knowledge, then they're misusing science. And it happens a lot, even by scientists and even some of the so-called best scientists can get wrapped up in thinking that their scientific conclusions are the law, immutable law. Okay, so as we understand more, we are continually interrogating hypotheses and theories. And that's one of the strengths of science, the ability to re examine our premises, the ability to reformulate our ideas. But it requires that the ground that we're standing on is always tentative, and that can be very uncomfortable um, for people or certain bits of knowledge. Okay, and so let's go over some examples of scientific hypotheses to maybe sort of show you the differences in the types of knowledge that are generated from ideas. And so this first idea, this first hypothesis, God, an omniscient and omnipresent being who existed before time, created the universe, right? That's a hypothesis. But it's not a scientific hypothesis because it is not testable and it's not falsifiable, for several reasons. And I won't go over all of them, but one of the reasons would be, how would human beings who operate um, operate within the dimensions in which time is one of the things we're subject to, how would we create a space outside of time to see whether or not there is any sort of consciousness that exists there, right? And then another limitation of this hypothesis that doesn't make it scientific is that, how would human beings be able to test for omniscience, which would be uh, knowing everything that there is to be known? Certainly human beings don't know everything, or any one human being, or even our collective knowledge can't account for everything. And so how would human beings who don't know everything be able to tell the difference between 99% of everything and 99.9% of everything, right? And so this hypothesis may be true for some people. It may be true sort of in general, but it is not a scientific hypothesis because it can't be tested or falsified. And that doesn't make it an irrelevant hypothesis. It doesn't make it not a useful hypothesis, but it's just not a scientific one. Okay, and this particular hypothesis, and hypotheses that sort of deal with the realm of the um, supernatural, um, oftentimes you'll see scientists doing a problematic thing and saying that because this idea is not scientific, then it's not useful. One of the most famous scientists who likes to make that argument is Richard Dawkins. And well, I'll just leave it. I'll just leave it at that. He likes to think that there is scientific evidence to disprove this idea. I personally happen to disagree with him, not because I hold this hypothesis as true or false, just simply because it's not a scientific question. And he, like a lot of scientists, try to apply scientific criteria to an idea that simply is outside the realm of science. Okay. So the second hypothesis, eating a low-fat diet decreases your risk of cardiovascular disease. Now, this is certainly a highly contested, highly debated hypothesis, but in fact, it is a scientific hypothesis. There are ways to test and falsify this idea. You can take a population of people and feed them a low-fat diet, and try to control for the other factors that might increase cardiovascular disease, and then feed another population a non-low-fat diet and see what the outcomes are. Now, this is a difficult hypothesis to test because there are so many other factors that could influence cardiovascular disease besides a low-fat diet, and there are ways around, limiting the influence of those factors. But this is a scientific hypothesis. It's something that can be can be tested and falsified. All right, and this last one, Dune is the greatest science fiction novel of all time. And certainly this is another highly contested idea, but it is not scientific, simply because the term greatest is something that is highly subjective, right? And so how do you define greatness? And then how do you get enough people to agree on what greatness is? And then how do you relate what is a work of this work of fiction that is Dune to that greatness that you have defined? Okay, and so this isn't a scientific hypothesis because it can't be tested, and because it can't be tested, it can't be falsified. Um, Now, you'll hear people in arguments or any argument saying, well, that's false and that's incorrect. But greatness, of course, is one of those things that's very subjective. It's very personal. It's very culturally determined. And so only one of these three hypotheses is scientific, and that's the one in the middle, because it can be tested and falsified. All right, so here are some ones that are maybe a little bit more tricky to recognize, but let's go through it. So the average global temperature has increased steadily over the last 50 years. And, perhaps 100 years ago, 300 years ago, this was not something that could be tested, simply because human beings, weren't keeping global temperature records for a period of 50 years. But we do have the technology um, and are sharing knowledge across the globe that we can actually look at this. And so this is a scientific hypothesis because it can be tested and falsified. This idea, global warming will result in the extinction of 90% of life on this planet. Now, this may seem like it's not a scientific hypothesis, but ultimately, um, we will be able to determine this, but we have to define our terms, right? And so, what is global warming, and then will result, and then the question would be, well, when would global warming sort of end or reach its apex? And then we can look at, the number of species that human beings know about to determine whether or not only 10% of what is present currently remains whenever global warming has reached its apex. Okay, but this is a scientific hypothesis, and one of the ways that science comes to conclusions about these things is to build models, is to project into the future. Because of the technology of being able to model different outcomes, we can create those models, put the inputs, and then come to a conclusion about certain ideas. And then, of course, ultimately, we can test that model based on what actually happens over time. But this is also a scientific hypothesis. Okay, this last one. At humanity's current rate of fossil fuel consumption, we will exhaust known fossil fuel resources by the year 2300. And again, this is another sort of scientific hypothesis that ultimately will be able to find the final bit of definitive evidence when this year occurs. But certainly we can build models in the meantime based on what we know are the fossil fuel consumption rates and what are the fossil fuel stores, and predict when fossil fuel resources are going to run out. And so this idea can be tested and can be falsified either through models and projections or ultimately when the year 2300 strikes. But of course, none of us are likely to be around at that time. Okay, so just having some images here and driving this point home about the realm of science and what science is trying to answer and what science is able to answer and what science isn't able to answer. So if you're looking for scientific hypotheses and answers to those questions and evidence for that, a place like this is probably not going to be the place where you want to go for scientific knowledge. But again, what's important is to not assign value judgments to either the fact that science answers certain types of questions and different belief systems and religions don't, and vice versa, which is something that scientists and people who are not scientists by profession and are religious argue about. And of course, there are scientists who are religious. Um, but it's important to remember that these different realms and these spaces, we're asking and answering different types of questions, and that's okay. We oftentimes don't do a good job of being okay with the different types of questions that are being answered because oftentimes there's a lot at stake about answers to these questions. But this is not a realm. This picture, this church is not a place where you're going to find a lot of scientific knowledge, and the same with science. You're not going to find a lot of you're not going to really find any answers to the questions of things like, why do we exist, right? Um, and what led to the Big Bang? Who created the universe, or what created the universe? These sorts of things that science just simply cannot answer. What happens to us when we die? Um, why do we die? Those are, may or may not be important questions to you, but science can't answer those questions for you. Okay, so it's important to recognize the distinction, and also not um, throw out either realm of knowledge simply because it is not the other. And of course, debates like this, who's the greatest basketball player of all time? I mean, obviously, if you want to get an A in this class, you're going to say the person on the left, because clearly LeBron James is the greatest basketball player of all time, and Michael Jordan is the second greatest basketball player of all time. But of course, this is also not a scientific question. Um, and if you're a fan of sports or a fan of basketball, then this is something that, many of us really enjoy debating. And it's a debate that happens quite a bit. But ultimately, there isn't a testable and falsifiable, um, answer to this question, even if you could, pit these two people against each other in the prime of their career. You still wouldn't be able to find a definitive answer to that question, because what people define as greatness may differ. Um, and so certainly they do when we're talking about these two players. But seriously, LeBron James is better than Michael Jordan. That's that'll be on the test. I'm just kidding, it won't be on the test. All right, so the take home message for this section when we're talking about science, first, is that everyone does science, and we're doing it all the time. We are all testing and trying to falsify different ideas and hypotheses. Okay, and so science is concerned with ideas that can be tested and falsified. And other ways of knowing and other areas of knowing, like religious um, ways of knowing, are questions that are not scientific. They simply aren't. There simply aren't questions that need to be tested and falsified. I mean, certainly they can be tested, um, and people can find evidence that they think might be falsifiable for that particular idea. But a religious idea or idea outside of science doesn't need to be both tested and falsified, and that's okay. There's nothing wrong with that. But it's important to recognize the differences in what these bits of knowledge are trying to answer. So in science, theories are not the same as ideas. Okay, even though in a lot of the language in which people are talking about science, they don't make this distinction, and that's something that takes practice to recognize. And so that conclusions that are reached by the scientific method don't necessarily undermine the scientific method. And so if there's a scientific idea um, that, for example, that Homo sapiens evolved from a common ancestor with modern day chimpanzees and bonobos. Right now, that's a scientific idea, but it may be that Homo sapiens evolved from an species that came to Earth on a meteor, or any number of things. And if we find evidence to support that, maybe Homo sapiens originated on Mars, and we traveled here in some form. We might find evidence for that in the future, but that doesn't undermine the scientific method, the process of false testing and falsifying ideas, just because we find evidence that doesn't support hypothesis. And so it's important to remember that we treat any scientific statement, any scientific idea, hypothesis, or theory as if the person were always saying before they express this idea, to the best of our knowledge, we think. Um, and that's one way that we can kind of begin to do a better job of understanding science and what science is saying. To the best of our knowledge is a really important caveat. Okay, and so we question the evidence and whether or not it supports the conclusion. And that's the really important thing with any scientific idea, is to, accept that somebody is saying something, and say, okay, I'll accept that this is an idea that you're offering, to the best of your knowledge. Well, let's examine the evidence. And oftentimes, when debates about science happen outside the realm of science, people want to, um, debate the idea itself, right? Instead of looking at the evidence to support it. And so we're going to get some practice in that when we talk about scientific ideas, and I'll be trying to help, desocialize you to the ways in which you may have heard science talked about, because it's oftentimes incorrect and problematic and leads to a lot of arguments that don't need to happen. Okay. All right. So I want to take time now to move on from science to talk about the foundations of biogeography. We're going to talk about some of the original formal European founders of biogeography, as well as people from other areas. Um, and this, again, is a way to kind of orient us to the content that we're going to be talking about later on in the semester. All right, so we'll start with the foundations of biogeography. And this is a picture of um, one of the first European biogeographers. Some of you all may think that this is a picture of, or a painting of, Charles Darwin, but it's not Charles Darwin. It's somebody else. So a gold star if you know who this is. So when we're talking about biogeography, it all begins with observations. And this is one of the things that all bits of knowledge, not just scientific knowledge, but all bits of knowledge begin with observations. Human beings perceiving their environment, not necessarily through sight all the time, but just perceiving the environment, whether it's through our five senses, whether it's through our emotions, whether it's through different ways. We make observations and then decide what we think about those observations. So biogeography, as a field of studying um, where life happens, and why and when, has been around for a while, but formally as a field of study only since about the 1970s. So maybe you all have, maybe your parents were born in the 70s, or your grandparents were around before biogeography became a formal field. But then, of course, the question is, what do you need to be a biogeographer? Right? And biogeography is within the realm of science, and so we know that everybody is capable of doing it. But what's important in making observations, and particularly determining why life occurs where and when it does, is you need difference. You need different places, and that could be one side of the yard versus the other side of the yard, or one side of the continent versus another side of the continent, or one side of the galaxy versus another side of the galaxy. But you need contrast, you need difference, you need different places, you need different geography, and you need different organisms. And of course, all one has to do in the world is go out and just observe and see that there's all sorts of variety of different organisms and different things that we can see. And of course, if you're going to be a biogeographer, I mean, being curious about these things is really important, right? If you observe, part of observations is being curious about why something is the way that it is, right? Why does one flying thing have these bright colorations, and another flying thing just has one color, right? So you have to be curious about that. And certainly, if you're thinking about exploring new areas, areas that you're not familiar with, and making observations about the organisms that live there, you need to be brave, because there are many organisms that could end up causing you harm. You think about the first human beings to come across a spitting cobra. Right? A spitting cobra is a dangerous organism to human beings. And to keep encountering that organism, you had to be brave. To make observations about a spitting cobra as a human being, you have to be brave to do that. So those things are important. And then, of course, you need a way to document those observations. And for most of our history as a species, those we documented those things not necessarily through writing down all of our observations, although early humans did do a form of that. But we documented these observations in our own minds. We documented them in our teachings. We documented them in our stories. Um, but a way of passing on the knowledge, a way of passing on our observations and our curiosity is really important. Okay, and so when we think about the arc of human observations and the arc of biogeography, there's a really important inflection point, a really important point in human history where human beings begin to live in a fundamentally different way. Um, and I'll talk more about that, but I want to make two distinctions or sort of two dividing points in the ways in which human beings express their biogeographic curiosity and knowledge. And one is through indigenous perspectives. And those ways of living um, much more closely resemble most of human history. When we think about indigenous people, indigenous human beings, so not necessarily in a modern sense, but people living within a local geography. And that doesn't necessarily have to be a small area, because we know that many indigenous people travel across continents or across wide spaces um, in search of food or to seek out other human beings or other areas, but not necessarily being concerned. Indigenous lifeways for much of our history as Homo sapiens, as human beings, we were not concerned about conquest. We were not so concerned about uh, amassing lots of surplus food and then turning that into wealth. Okay, we were living in a way that was much more connected to um, our local ecology, our local biogeography, um, and being in good relationship with other organisms, and less about trying to dominate and control. Okay, and so this is really important to recognize because one, because there are many indigenous groups that are still living in this form, in this fashion, and many more who have been impacted by what we might recognize or call civilization, human civilization, um, in a negative way, and would like to get back to these life ways. Okay, and so when we think about indigenous perspectives in biogeography, or just indigenous perspectives in ecology in general, there are much more intimate relationships with non-humans, and not just non-human life, but just the environment, right? And we think about our own lives and how there's much less intimacy with that. And part of the goal of this course, as particularly with Organism of the Week and some of the other things that we're going to do, is to connect you um, more to your environment. There's a lot that we walk by in our day-to-day lives that we don't understand or that we don't have a relationship with, and that's something that's a big difference for human beings as a species. So when we think about indigenous perspectives, and we're going to come back to those differences, we think about intimate relationships and others, non-humans, as relatives and not things or an it. Right? If we pay attention to the ways in which we talk about um, other species, we oftentimes say, "What's that thing over there?" Or if we see an organism, we say, "What's it doing?" And that is a something that you don't see, the language that you do not see a lot in many indigenous cultures, and not just indigenous cultures in what's now called North America, but anywhere you find human beings living in intimate relationships with the organisms and the spaces around them. And because of that intimacy, there's a deep functional knowledge of the local ecology, or the ecology that you're in relationship with. In the same way that being in an intimate relationship with another human being, you gain a deep functional knowledge of how they function, what sorts of things they like, what sorts of things they don't like, ways to support them, and ways to undermine them. Um, and so that's another really important feature of indigenous perspectives. And that knowledge is tied to the personal geographies, right? Being able to understand the world around you. And if you think about, if we were to go outside um, to wherever we are right now, how many different species could we name in our backyards or on our walk to wherever we might be going, or the place where we grew up? How many species would we be able to name? Um, and for many indigenous people whose cultures are intact, who haven't been negatively impacted by modern industrial civilization, that number is much higher than it is for us. Okay. And so, if you're interested in learning more about indigenous perspectives, particularly the conversation between indigenous wisdom and so-called scientific knowledge, this book I can't recommend highly enough, by a botanist named Robin Wall Kimmerer, and I think I'm going to have you all listen to a podcast with her on it. But she does a really great job of um, putting putting indigenous knowledge and indigenous wisdom in conversation with scientific knowledge in a way that's just fabulous. So I can't recommend that book highly enough if you're interested in reading it. Okay, and so this inflection point, when we start to see human beings living in a less intimate, less local, um, less relational um, relationship with other species and the environments, um, it's about 15 to 12,000 years ago, sort of across the globe, we see these civilizations, these different civilizations begin to pop up. And out of these civilizations, and I'm just going to name a few here, there are thinkers, people who are making observations and recording their observations across different cultures. And so Zhuangzi, who is a Taoist philosopher in what's now present day China, part of his intellectual pursuit was uh, naming the different stages of life and understanding that life exists in a state of change and transformation. He was observing things like caterpillars turning into butterflies, or caterpillars turning into moths, right? This transformation and change, or the energy of a prey individual feeding and supporting the predator, and that energy, of course, being transferred. So he was one of the first people within these types of societies to start cataloging this knowledge. Okay, and of course, Aristotle in Greece wrote a book, The History of Animals, and classified organisms according to their complexity and their structure. And of course, human beings were the most complex and the pinnacle of creation, whereas other organisms like worms or roaches or leeches and things like that were simpler, and I'm using air quotes here, simpler organisms and not as complex, and of course, therefore, not as special. Aristotle also observed and recorded that animals were designed for a purpose, so that certain features in organisms functioned in a particular way that was important for that organism. Organisms with sharp teeth use those teeth to acquire food. Organisms with sort of flatter teeth use those teeth to um, consume plant material. And in what is now present day Iraq, there was a biologist and philosopher by the name of Al Jahiz, and he wrote the Book of Animals. It's actually a cover of that book. And he was one of the first people living within these types of civilizations to classify species and then, of course, write those things down. Um, and he was one of the first to describe food chains. And I say describe and write down and then transmit that knowledge. And so, in a particular way. And one thing that you'll observe from all of these individuals is that they're all men, right? And that they certainly weren't the first ones to conceive of these ideas, and likely not the first people to write their ideas down or to document their knowledge. Um, but they happen to be from cultures that did a very good job of spreading their ideas across other cultures, and no doubt. And we know this from history, that each of these cultures, along with many others, um, have subjugated and eliminated other peoples and other bits of knowledge. Okay, and so that's one of the reasons why when we talk about these thinkers, we kind of get into this lazy habit of saying like they're the first people to do these things, but they weren't. They were happen to be members of cultures that could spread their knowledge, and their knowledge dominated kind of our understanding. And so we need to push back against that. And this is why the social sciences and the humanities are really important to put this knowledge into context. But just some of the thinkers around this time that have shaped the ideas in the field of biogeography, for better or for worse. Okay, and so then moving forward to about 250 years ago, the number of species that the dominant cultures on this earth uh, were able to describe or had described is was only about less than 1% or about 1% of today's species that the collective human beings have described. And there's a big reason for that dramatic increase over the last 250 years. Um, and we see that around the mid 18th century, the 1750s. And the question is why? Why is there this sort of explosion of the collective knowledge, or at least the curated knowledge of human species? I mean, certainly human beings have traveled all across the globe at this point, um, but the things that the different human populations across the globe had not been collected um, into kind of this Encyclopedia Britannica set of knowledge that could be shared and transmitted across many different cultures. And so the reason why, what's happening around this time? And of course, the answer is European global colonization. It was a very dramatic event that certainly was taking place before that. But around the mid 18th century is when things really begin to pick up, and that the knowledge that was being collected by European colonizers was really beginning to be curated and understood. First, of course, within European culture, and then, of course, throughout history, being transmitted to other cultures. Um, but the simple act of crossing the Atlantic Ocean, right? Um, and uh, Certainly human populations had crossed the Atlantic Ocean before and had crossed the Pacific Ocean before. But crossing the Atlantic with the expressed idea of colonizing new lands and collecting uh, different species and different cultures was a thing that really dramatically increased the knowledge of European biogeography, and of course with the organisms that Europeans brought to the so-called New World, was a big increase in knowledge for those who were there. And so the terms New World and Old World were introduced. And the reason why those terms are very dominant and still present today is because not only did European powers collect non-human species, but they collected humans and subjugated and murdered and killed and destroyed many cultures. And they were we all are the inheritors of that conquest, and with that comes terms and terminology that may not be, and in fact is not necessarily the best way to describe things, but it tells us about the cultural relativity of New World and Old World, and certainly for indigenous people in what's now North America and South America and this part of the world. For them, Europeans were new. That was a new world to them, and that their old world was the world that they knew. Um, and so again, it's important to understand the relative context of the knowledge that we talk about. And so spices and human beings weren't the only things being trafficked by European global colonization. It's certainly, new species of food was really important. And one of the things that's really fascinating to think about, and maybe we can think about some of the European foods that many of us are familiar with, and we think about Italian cuisine, right? And how important the tomato is for Italian cuisine, and actually how important the tomato is for many cuisines. But for the continents on the other side of the Atlantic from where we are right now, tomatoes weren't introduced to that part of the world uh, until about the 1500s. Tomatoes are native to and are endemic to this part of the world. And so for up until the last maybe 500 or 600 years, tomatoes were not present in Italian cuisine and many other cuisines. We think about the potato and how important it is for what's now considered the United Kingdom. I mean, the potato is another species of food that's native to this part of the world, or this half of the world. Um, that wasn't present in Europe, but we think about dishes like fish and chips and the potato famine, um, and how important those foods were. But they're relatively recent things, okay? And so there's this great biogeographic exchange between continents and cultures. And of course, that exchange was very violent and not at all equitable. Okay, and so when we think about European biogeographers, um, the explanatory toolbox for most Europeans who are traveling across the Atlantic and traveling to far-reaching spaces to explain what sorts of things they were seeing was Christianity. That was the dominant way of knowing of Western Europe. And so you run into problems when you have that as your only tool in your toolbox for understanding things, right? And so the problem was, the Bible didn't mention bonobos, which are another term for them is pygmy chimps, or Komodo dragons or kangaroos. I mean, imagine growing up your whole life never having seen a kangaroo and getting on a boat and going to Australia, or what's now considered Australia, and seeing a kangaroo. Like, how do you make sense of that? It would be as strange as if you hopped on a spaceship and went to another solar system and saw a creature that we can't even conceive of right now, right? 25-foot reticulated pythons that people from Europe were going to. And so how do you explain that? It becomes very difficult. And we'll talk about, some of the ways in which the way of knowing, the religious way of knowing, Christianity, runs up against issues, and also sort of explains why there is still conflict between religion, or potentially between religion and science. So, the question that comes up for many Europeans is, what was God doing in these places? Why are there kangaroos and Komodo dragons and reticulated pythons in these parts of the world and not where I come from? And there are all sorts of horrible answers that Europeans came up with for why that was. All sorts of things that result in well, this is a forsaken place, right? And this is not something that's necessarily unique to Europeans traveling to, historically Europeans traveling to different places and thinking that a place, because of its people and because of its species, were forsaken. That's a common human thing to do, not necessarily exclusive to Europeans. But it does create, the point is that it does create a schism in one's thinking, right? You need to explain this. What was happening here? And why didn't God mention his plans before? Like, clearly I can see that these things exist, but my toolbox says or doesn't mention them. So why? Why is that? Um, Excuse me. And maybe one of the most famous biogeographers, Linnaeus, who is the creator of the binomial nomenclature, um, attempted to classify organisms, right? So one of the things that's curious is, well, like, I know we have taking, large reticulated pythons. Linnaeus might have thought to himself, or other European biogeographers might have thought to themselves, well, we have snakes here. I know what a snake looks like, and this looks a lot like a snake. So I wonder how these two things, these two species are related. These two organisms are related. And so one of the ways that you can do that is through naming things. And the name you give it denotes how it's related. So Linnaeus came up with a binomial nomenclature, Ursus americanus, which is the Latin name for black bear. And so all organisms are created at the same time on an island with different habitats. And this is the way that Linnaeus explained many of the creatures, many of the organisms that he had never seen before. That this must have been part of creation. This must have been part of God's plan all along. And there must have been, the Garden of Eden was an island, and there were different habitats on that island. And God created, these creatures that I'm now seeing in these places and not in mine. And, I just didn't know about them. Um, and so, over time, Linnaeus thought that animals colonized new lands as the oceans receded. Right? So we start from this idea that there is a Garden of Eden and God created all of these creatures at the same time. And then over time, oceans receded and those organisms colonized new areas. So another European geographer who is a contemporary of Linnaeus, Buffon, who's French, he was critical of Linnaeus. And, here we see the scientific process at work. We see somebody propose a hypothesis and somebody say, well, where's the evidence for this? And in fact, I have some evidence that does not support your hypothesis. And so one of the things that Buffon observed is that similar environments, so deserts in different parts of the world, have distinct organisms. And so if all organisms were created at the same time and um, were created in their own environments, then, if I look at a desert in one place, let's say, the Gobi Desert in what's now the Mongolian plateau versus what's the Sonoran Desert in what's now considered North America, then I should see the same organisms according to Linnaeus's hypothesis. But Buffon said, well, wait a minute. You have Saiga antelope in the Mongolian desert, but you don't have that same organism in the Sonoran Desert. And there are rattlesnakes in the Sonoran Desert, but if you look at the Namibian Desert, I don't see the same rattlesnakes. And so that was something that he observed, and that was a bit of evidence that did not support Linnaeus's hypothesis. And another issue that Buffon had with Linnaeus's idea was, how could organisms who were clearly adapted to certain environments survive in order to travel through different environments to another area where they would be able to survive, right? And so how could a mountain goat, who was created at the top of a mountain, make it to a mountain in a different part of the world by traveling through the jungle? There's no way a mountain goat would have made it through the jungle with all of the species that are there that are adapted to it. And so these are two observations that Linnaeus or that Buffon made, and said, "No, Linnaeus, I don't think you're really right." But his idea was not much better. And so he said that all organisms originated in northern latitudes, and as they traveled um, south, uh, they adapted to different environments, and some stayed in those environments, and others sort of continued to move on. So there was this general southern migration over time. Uh, so we'll talk about the limitations of Buffon's idea, but the one that still has lots of evidence today is that in isolated environmentally similar regions have unique groups of mammals and birds. It's Buffon's law, and it is called a law because of the overwhelming evidence to support it. But we may find that Buffon's law um, does not hold up the more species that we find, or we may find that Buffon's law is only applicable to planet Earth, and if we travel to a different planet, we may see a different pattern. And so one way that we can see Buffon's law is that South Africa's coastal biology, which is a very similar environment to the Northwest or South Africa's climate and ecology, is very similar to the northwestern part of what's now the United States, but they're very distinct organisms in those two similar environments. And so for plants, Buffon's law also applies, and it was confirmed by Forster, who was somebody who was born a generation after Buffon and Linnaeus. But the take home here is that Buffon's law is really important for biogeography, a really important principle for biogeography, that similar climates and seemingly similar environments have distinct organisms. Um, okay, and so we think about these other Western European biogeographers, Humboldt, who was several generations after Linnaeus and Buffon. He's a very, very famous biogeographer. You probably haven't heard of him, um, um, but if you travel to South America, Central America, you will hear a lot about Humboldt. And in fact, there are a lot of national parks and um, ecological preserve spaces that are named after Humboldt, and that's because he spent most of his time in that part of the world making lots of observations about the variation in plant species. And he was one of the first European biogeographers to talk about zonal variation based on climate. And so Humboldt would climb these large mountains and catalog the different species as he moved up in elevation, as he changed climate. And this is a really important biogeographic principle, and he sort of outlined this principle in essays on the geography of plants. Okay, so he um, didn't call himself a biogeographer, but he was essentially studying biogeography, laying one of the foundations for the field. And so, a question that I would ask is, why do you think he chose plants? And of course, the answer is when you're cataloging a lot of species and you're relating it to climate, it's a lot easier to observe those changes when the organisms don't move as quickly. Um, Whereas, finding out or determining whether or not this pattern holds true for organisms, animals that can move around, it can be a little bit more difficult. But of course, this principle does hold up with animals. Um, and so, these individuals may have made really important contributions to scientific knowledge, and certainly sit at their many of the things that they described sit at the foundations of biogeographic knowledge. But as is often the case, people are complex, right? Um, and if any human being, no matter where they're from, isn't careful, then certain unscientific ideas can come into play and be passed off as scientific ideas. And so some of the things that Buffon said, which are not scientific and deeply problematic, is man is totally a production of heaven, but animals, in many respects, are creatures of earth only. And this isn't necessarily a problematic idea in and of itself, um, but it is also not a scientific idea, right? Because how can you test whether or not you're in heaven? And another, idea that animals, in many respects, are creatures of earth only. And how can anyone know what we call animals? And certainly, biological evidence points to or suggests that or shows that human beings are animals from a biological standpoint. But if you were to say non-human organisms, how do we know that those organisms are creatures of earth only? This question of like, do dogs have a soul or something like that? I mean, we don't know what happens to those organisms when they pass on, and they may go to another realm. Okay, so this is not a scientific idea or a scientific hypothesis. Um, it's not necessarily problematic, except for the fact that Buffon used this idea to justify some horrible things that uh, people from the culture that he grew up in did to animals or non-human species. Here's another unscientific idea that is deeply problematic, right? So in this new world, there is something that opposes amplification of nature. There are obstacles to development, thinly peopled with wandering savages. Okay, and so there's all sorts of value judgments in this statement. And so here we have somebody from a particular culture who is looking to distinguish his culture and himself from the people, the human beings, and the environment that he's coming to. And no doubt, Buffon is unnerved and maybe a little bit intimidated and trying to process this new space. And it's clear from this quote that he didn't like necessarily what he saw. But of course, we know that the part of the project of European colonization was not just to explore new areas and exchange on equal terms with the human beings and the other species that were found, but it was to come and take and to dominate and to destroy if um, uh, those who were there resisted, and that's exactly what happened. And so we can begin to see this kind of rationalization of the project of colonization. And so this is where things that um, are not scientific ideas, not scientific hypotheses, get get dressed up as a scientific idea. And we see, from history that many people from colonizing cultures try to use science to justify the horrible things that they did to people. But that's not science, and this idea isn't science. It's just a way to rationalize domination over others. And so another person, John Muir, who is a towering figure in um, conservation in this part of the world and throughout the world, also had some very problematic ideas about different peoples that are there. So as to Indians, and he was referring to what Europeans came to call indigenous people here, most of them are dead or civilized into useless innocence. Um, and so this again is not a scientific idea. Most indigenous people, when John Muir said this, were not dead. Um, and civilized into useless innocence. That's a very sort of subjective way of thinking about things. And in fact, John Muir, it's not clear whether or not he did know this and just offered a false narrative, or if he really believed this and didn't know. But he is responsible for the establishment of Yosemite State Park and Sequoia State Parks or national parks. And he and a number of other um, descendants of European colonists came to these areas and thought that they were so majestic and so beautiful and so impressive that they had to be preserved. And what they didn't either know or want to know was that the beauty that they observed, the pristineness, the abundance, was very much a product of the relationship that indigenous people had with the species in that area. Um, but again, we can see these unscientific ideas come into play because the people who were saying these things, particularly the last two statements, were part of a culture that was um, interested in taking indigenous land and doing with the land and with the species there what they wanted to, and were not interested in sharing or being in relationship with the people, or being in good relationship with the people that were there. So it's important to, and this is why it's important to understand the differences between scientific ideas and unscientific ideas, and to be able to recognize something as science and not science, and to resist the idea that something that's said to be scientific, even if it has evidence to support it, doesn't necessarily make it the end all be all. So we can learn from these observations, these unscientific ideas, is that scientists are human beings, and they are informed by the cultural beliefs, the concepts, and the goals of the culture that they come from. And so, if you are coming from a culture that, in a particular point in time, is interested in conquest and colonization, then you begin to rationalize certain ideas and certain value judgments that are not scientific, um, to be able to do the things, or to be able to um, uh, let's see, what's the right word? To be able to um, be more comfortable with some of the things that your culture is perpetuating. Um, and again, this isn't something that's unique to European culture. Um, we're all susceptible to the cultural biases and cultural beliefs that we have, and what it is that our intended goals are with um, the relationships and the knowledge that we seek. And so cultural beliefs are often rooted in or seeking to gain power over um, other people, other human beings, other species. And this is one of the things that is unique to, or one of the important characteristics of not just European culture, but cultures that we would maybe say are part of, or that have led to modern civilization. Um, and it was a big change from how human beings have existed on this planet for a really long time, for most of our history. We were not interested, no matter where we came from, we were not largely interested in gaining power over other species and gaining power over other human beings. We were certainly wanted to preserve our cultures and to maintain our cultures and our identities. But we weren't interested in dominating and taking or evicting for all time or subjugating other peoples. Um, and so we have to be especially careful when we live in cultures and we come from cultures that are seeking power over others, whether that be human beings or other species or environments. We have to be careful that we're not claiming um, ideas or practices that come out of that as scientific, as things that can be tested and falsified. Um, and that's an important distinction. So the beliefs about the cultural constructs, whether it be race, whether it be gender, whether it be religion, in relation to others, they're never scientific. If you're making value judgments that men are superior to women, or that this way of believing is better than that way of believing, or that this particular group of people, ethnicity or race is better than another, then those simply aren't scientific ideas. They are certainly important ideas, not necessarily because they are morally defensible, but they're important because they are the things that have largely dominated the reasons or the relationships between different groups of people. So, these ideas like the best way to eat red meat is well done, or always give birth in a hospital, or always say bless you when someone sneezes, these are cultural beliefs that are not scientific. Um, but that, again, that doesn't mean that they're not important. The cultural value of a thing is deeply contextual. And because it's deeply contextual, the evidence that supports the idea is not scientific because it can't be understood outside of that culture. You have to you have to be rooted in that culture. So again, we need to be careful about what we're defining as science and what we're defining as not science, and then be careful about the reasons why an idea we are offering is important. So to get back to how this pattern that largely the pattern of thinking and making observations that's rooted in Western European colonization are these observations that organisms change over time. And there's one bit of evidence for that really kind of blew the doors off of the biogeographic knowledge within Western European thought. And of course, that is the presence of fossils. Right? So, the beginning of the 19th century in Western Europe, people were discovering um, these creatures, these organisms that were present in the rock. Um, and it's really interesting. I mean, we see the rise in mining, the rise in the technology to break open the earth and to harvest these different resources that are there at a large industrial scale. We see an increase in the discovery by certain cultures of these fossils. And so, again, what do you do if you're the only explanatory tool you have in your way of understanding the world is a religious text that doesn't mention, and this is a skeleton, I think, excuse me, of a plesiosaur. What do you do with that? Maybe you say, oh, this looks like a water dragon, because, excuse me, because of the stories that I've heard and the folklore that I've heard, that this is what my ancestors must have been talking about, this dragon. But again, it becomes a point where you're confronted with physical evidence that requires you to rethink your premises, to rethink your knowledge base. Okay, and so the fossil record becomes a really important thing that has to be explained by folks in Western Europe. And there's different cultures all across the world that have had experience and had been exposed to fossils and have different ways of explaining that. But because biogeography comes out of a Western European epistemology, we're talking about how the fossil record was understood within this dominant culture. And so, clearly these organisms are no longer alive, right? There aren't plesiosaurs, unless you count the Loch Ness Monster. There aren't plesiosaurs that are roaming the earth. There aren't Tyrannosaurus rexes that are roaming the earth. And so that begs the question, these organisms lived a long time ago. And for many folks, there wasn't any documentation of these organisms. And so, how far back did life go? And, the question is, well, maybe, life is older than what what the time scale that's outlined in the Bible is. Maybe the earth and life is older than 6,000 years, right? And another thing that was, very difficult to explain is that many of these organisms that clearly are adapted to living in water were being dug from the sides of mountains, right? And so, why are there fish fossils in my backyard? This place has been land for as long as I can remember. Uh, you know, it's been land, not covered by an ocean, for as long as anyone in my family can remember. And so, how did a fossil, how did an organism skeleton that clearly is a fish or clearly is an aquatic organism end up in my backyard? And of course, the idea starts to come into play. Well, maybe dry land wasn't always here. Um, how far back does time go? Um, and so, in answering these questions, we get a paradigm shift. And Charles Lyell, who is a geologist and a paleobotanist, um, attempted to answer these questions, right? And so he hypothesized that mountains have grown and eroded. He didn't have a mechanism for how mountains grew. Um, Sea levels changed, didn't have a mechanism for how the sea levels change, what would cause the sea levels to change. Excuse me. But he was accepting the evidence that he saw in front of him and saying, like, well, clearly, this space wasn't always mountain, and the sea covered this land where I'm finding these fossils. But he still had to contend with, and he still had within his toolbox, this Genesis textbook, and I put that in quotation marks, as the Genesis textbook, the textbook that is the Bible, the book of Genesis. And so, in order to reconcile these two things, he said that there were multiple creation events, right? So maybe the earth is older than we thought. And that was a very, very controversial idea for somebody to propose, this idea that maybe the Bible, saying that, the earth was created in 7 days, and that if you look at the genealogy of the men who are named in the Bible, that, time goes back, and maybe life has been here longer than what the Bible says. That's a big, 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 big shift. And Lyell was not liked by a lot of members of certain communities for suggesting this and saying that the evidence points to this. Okay, and so that was a big paradigm shift. And the reason why Samuel L. Jackson is here is because shortly after that, there was another paradigm shift. So hold on to your butts. And of course, this is a screenshot from one of my favorite movies, Jurassic Park. And Samuel L. Jackson plays a character who says this a lot in the film: "Hold on to your butts." And so, if you were a person living around that time and you thought Lyell's idea of the Earth being older than what the Bible says was shocking and made you want to clutch your pearls, then the ideas that some folks put forward shortly after Lyell were really, really controversial, difficult to accept at first, and really shifted the way in which people thought about the Earth. And so the distributions of life are dynamic, meaning that they change, and they changed over space, and they changed over time. And so up until this point, many people thought that what existed, what they observed, the species that they observed, were had always been there, and that life had largely not changed. That there was no such thing as evolution. There was no such thing as organisms changing over time, because God created them in the way that they exist today. And so the way that they exist today has been the way that they've always existed, both spatially and temporally. But there were four scientists, biogeographers, Chuck, Joe, Phil, and Al, who challenged this idea through their travels, through the observations that they were making. And so two of the biggest ones, Al Dub and Chuck D, Alfred Russel Wallace and Charles Darwin. You've heard of Charles Darwin, you probably haven't heard of Alfred Russel Wallace. And we'll talk more about them in detail in next week's lecture. But these two biogeographers formulated the theory of evolution by natural selection. And what's fascinating is that they formulated this theory, and at the time was a hypothesis, independently of each other. And so they were both from England, but Charles Darwin, as many of you know, traveled west to what's considered the New World, and Alfred Russel Wallace traveled east. And so they almost crossed paths in the Pacific Islands, but both got to their westernmost and easternmost destination and then came back to England. And in their travels, they made lots of observations and collected a lot of specimens and came up with this idea, theory of evolution by natural selection, independently of each other. Really interesting. So both world travelers collected specimens. And in fact, Wallace was a much more prominent biogeographer. He made more observations of species, came up with a lot more ideas as it pertains to biogeography. One of the reasons why Charles Darwin stopped traveling as much as Wallace did was because he became ill in his travels. But many of Wallace's ideas still hold today, and I'll talk more about why you've heard of one and not the other. Coming close to the end of this, and then so, fast forwarding, we can think about modern advances in understanding life and how it's dynamic, both spatially and temporally. So we can think about the plate tectonics. And I mentioned that Lyell did not have a mechanism for explaining why mountains grew and others eroded. But the theory of plate tectonics, the concept of plate tectonics, and the movement of large bodies of rock across the surface of the earth was not really accepted until the 1960s. Okay. And so being able to explain the Rockies and the Appalachian Mountains and the Himalayan Mountains, we know that those structures exist on the planet, but until about the 1960s, it wasn't accepted. There wasn't a scientific mechanism to explain it. So we can think about genetics and the description and discovery of DNA and how it's transmitted. We think about Charles Darwin, who came up with the theory of evolution by natural selection. He didn't have a mechanism for how traits were passed on. He couldn't explain scientifically exactly why, and what was the mechanism that made offspring look like their parents. And that explanation came a bit later. And then we could look at things like spatial analysis, and that's why I have this picture here, these two pictures here. Spatial analysis is really important, particularly through GIS, global information systems, and being able to track how organisms move across the surface of the earth and even underneath the surface of the earth in aquatic environments. Can also really help us understand biogeographic patterns, why life occurs where and when it does. Okay, and so these modern advances have contributed to this body of biogeographical knowledge, and that's kind of the arc of what we're talking about. So really important to understand that arc and to understand the limitations and some of the pitfalls that have come throughout that. And it's really important to to be vigilant about the ideas and the conclusions that we come to and the evidence that we're building and what we do with that evidence, that we don't fall into problematic ideas and to seek to perpetuate power over others at the expense of their ability to determine how they want to live their life. And that, holds true for human populations as well as non-human populations. Okay, so a question of the week. So we ended this talking about evolution, and I mentioned it a number of times. And so the question of this week is, what is evolution? It is an extremely important idea. We're going to spend a large part of the semester talking about it and understanding it. But what is it? So I want you all to as you did for last week, get on the Google form or click the link in eCampus for question of the week, week 2, and answer the question. And I'm not grading for um, the correct definition of evolution or what is evolution, but what is it? Don't look it up. I want you to tell me what evolution is, how you define evolution, um, and we'll have a discussion about that in next week's lecture. Also, don't want you to forget the other assignments that are going to be due at the end of this week or before our next lecture is is released. And I have an activity for you. So, alien world on Earth. And so, what this assignment is you will be allowed to select from one particular organism out of a collection on eCampus. Hopefully, it's going to be something that you consider bizarre, that you've never seen before. And I want you to fill out the worksheet to describe it, to just use the skills and the prior knowledge that you have. And this is a way for you to experience what it was like for human beings to travel to different places and observe new organisms. And so there's a series of questions that I want you to answer about those organisms. Um, and if there's one within the folder that you do know what it is, then choose one that you haven't. Choose the one that is the strangest to you, that is maybe the most um, scary or the most repulsive or the most interesting. And do your best to describe what you see based on what you know, what's already in your head and not from a Google search. And again, I'm not grading on the correct answers, but just use your prior knowledge to answer those questions. Your first podcast will be available for you to listen to. There isn't a reflection for this podcast, but it is one that talks about the scientific process. And the content of that will be fair game for the exam. So you want to make sure that you listen to it because there may be a question or two on the midterm exam that pertains to this podcast. And the last thing to be on the lookout for this week is to check out the first organism of the week video. I will post that on Wednesday on the class YouTube channel, and it's a doozy. I was in my neighbor's backyard picking tomatoes and found something pretty gruesome and pretty amazing. So I'll release that on Wednesday for you to look at. And again, you're going to want to take a look at that because there may be a question on the exam that pertains to this video where you can earn bonus points. Okay? So thanks for listening. This was a long lecture, but you have the whole week to listen to it. But make sure that you get through everything and you're staying on top of your assignments, and that you're turning things in and staying on top of things this week and for the rest of the semester. Okay, I will talk to you all next week. If you have any questions or concerns or anything like that, just drop me an email. Alrighty, thanks.